Good afternoon and good evening to all our friends in the US, Israel, and wherever each of you is connecting with us from. My name is Ruby Shamir, and I'm the Executive Director of AFL in Israel. Today, I'm honored and happy to introduce you to our third webinar presented in cooperation with the Zuckerman Institute. The Zuckerman Institute was established in 2015 to achieve the philanthropic vision of Mortimer Zuckerman, to enhance collaboration and communication among the most promising scholars in science, technology, engineering, and math in Israel, the United States, and Canada. The Zuckerman STEM Leadership Faculty Program provides vital resources to Israeli universities, allowing them to compete with top North American institutions for the most promising candidates. The program facilitates the return of top Israeli scholars to Israeli institutions, cultivates world-class scientific talent, and in turn, attracts outstanding postdoctoral researchers from top US universities, thus creating a cycle of excellence. Faculty scholarships are given out every year to each of the 7 participating Israeli universities, including Bar-Ilan University, Ben-Gurion University of the Negev, Haifa University, the Hebrew University of Jerusalem, Technion Israel Institute of Technology, the Tel Aviv University, and Weizmann Institute of Science. Since the start of the program in 2016, 30 Zuckerman labs have been established in Israel. On today's webinar, we have 2 presenters, a Zuckerman Faculty Scholar from the Technion in Israel, Dr. Joseph Lefkowitz, and his US collaborator and colleague, Dr. Timothy Ombrello from the Wright-Patterson Air Force Base in Ohio. I'm happy now to turn to my colleague, Wayne Firestone, Executive Director of AFL in the US, to moderate the panel. Please, Wayne.
Ruby, thanks so much for that introduction of our panel today. It is great to see you back in Tel Aviv in your environs that you're used to. I know you spend a lot of time crossing normally back and forth over the Atlantic to visit with family. And we sort of take for granted and have taken for granted sometimes, certainly, our ability to do so. COVID has humbled us. We haven't been able to make as many of those transportation, take advantage of that as much, certainly over the past year and a half. We hope that will be getting better. But today's panel on high science that the Zuckerman Institute has allowed us to really explore in depth different topics is going to actually allow us to focus on transportation today and transportation of the future. So before we get to a more formal introduction of the panelists, I want to throw out a question to the audience. As you think about the forms of transportation that you use and have used over the course of your lifetime, which would you say has evolved most rapidly during your lifetime? The technology, meaning the speed and the efficiency. Is it a plane? Is it a cable car in San Francisco? Probably not the highest form of speedy transportation, but nonetheless, with transportation that you utilize or have utilized during your lifetime, what do you think has actually evolved the most quickly and changed in ways that you can actually feel it and see it? Because we'll be talking today about the underlying technology on a number of forms of transportation. We've seen over the past couple of months private crafts go into space. That's becoming increasingly more of a norm. We see large-scale infrastructure projects for bullet trains. We know that the electricity revolution of cars is introducing a new breed and a new form of cars. So please share with us where you are in the world, where you're connecting with us today, and what forms of transportation you have seen take the greatest changes. We're going to be discussing that today with two panelists who know one another and have actually been working and talking about these issues for many years, dating to their own graduate school experiences. Professor Joseph Lefkowitz is indeed a Zuckerman Scholar at the Technion, and he started his graduate work, actually initially his undergraduate work at Johns Hopkins in mechanical engineering, and then went on to get his PhD at Princeton, which is also where our co-panelist did his graduate work. And Professor Lefkowitz also did a postdoc at the Air Force Research Lab prior to joining the Technion. So he's pretty familiar with the terrain on both sides of the ocean, and we're looking forward to exploring that. His colleague, Dr. Timothy Ombrello, is the senior researcher at aerospace engineer at Wright-Patterson Air Force Base in Ohio. He did his bachelor's work in mechanical engineering at Cooper Union, went on to get his PhD in mechanical engineering and space engineering at Princeton, and he's co-authored over 70 peer-reviewed publications on the topics we're going to be discussing today. And I promise you, Tim, and we will not be cross-examining you on any of those 70 peer-reviewed papers today. Instead, we're going to give an opportunity for you and Joe. I'm going to call you Joe and Tim because that's what you call each other. And I know you're very informal with each other. We'll be informal with you today on our program. We're so excited to learn a little bit about your research and your work. But before we jump into the substance of your research, Professor Lefkowitz, maybe you could start with just a little bit of a personal introduction and how indeed you even ended up in a laboratory in Haifa after doing your work here in the United States.
Wayne, thanks for the nice introduction. You covered a lot of the basics. I grew up in New Jersey, and how I ended up here was a great and long road. Like you said, I did my undergraduate at Johns Hopkins and my graduate work at Princeton University. And I did postdoctoral research with Timothy Ombrello over at the Air Force Research Laboratory. But I've been back and forth to Israel, and as you mentioned, it's a little harder to do that these days. But I've been back and forth to Israel many times. And when I was looking for the next step for me, really, Technion had always been on my radar. It's a great university. Our department was just ranked in the new Shanghai rating at 17th in the world. And so there was an excellent opportunity here to come to Israel, to start a new lab, and I couldn't refuse. It's really an amazing place, Technion. And I'm just happy to be here every day in the sun near the beach.
Well, I'm sure you're taking advantage of that, and I'm sure we'll at some point talk about solar energy as well. Tim, sun is great, but you can't always use that on a rocket ship or other forms of transportation at night. Tell us a little bit about your journey and the work that you're doing today.
Sure. So in a similar fashion to Joe, I'm also from New Jersey, a little bit more western in the state from where Joe is from. But my path taking me to the Air Force Research Lab was really motivated by a strong interest in looking at aeronautics and aerospace and high-speed propulsion, which is predominantly where I work, the area that I work in. But a lot of that hinges upon looking at other creative means of enhancing a variety of different technologies. And that's what I've been kind of working on for quite a bit of time and enjoying it tremendously since then. So, and fortunately, we've been able to establish a nice collaborative working relationship between the U.S. and Israel through a country-to-country interaction, which has allowed Joe and I to work in a very fluid manner for the last, I think, 2 years now, and make some really great progress. So we're really happy to be here today, and thank you for the introduction and to have a nice discussion on this.
Great. Well, our folks who are calling in from around the world are referring to pneumatic trains and smelly buses that converted to electricity, electric bikes, electric cars, a lot of forms of transportation that began very modestly, and we are watching in sort of real time in our own lives how these forms of transportation are evolving or changing and becoming faster and more efficient, etc. So today I know we're going to get a little bit of a science lesson as to how and where some of that change may have been blockaded, and what the work that you all are doing is sort of doing to advance that, and indeed where this may be leading us. So I think you two are actually inaugurating one of our first co-presentations. So I want to give you a hearty kol hakavod and congratulations for being our pioneers at not merely presenting individually what you're doing, but sort of presenting together a little bit about your work. So we'll hope the Zoom gods are behaving today, and Tim, I think turn over to you first to at least run the presentation, and for you and Joe to share your insights on this work.
Excellent. All right. Thank you. So you should be able to see my title slide, Joe and I's title slide on here now. So our discussion today is on electrifying combustion and how plasma technology can accelerate the transition to renewable energy. And I'll let Joe take a moment to talk about this, but I guess I'd add one little piece on, is that Joe and I did meet through similar means at Princeton, meaning that we had the same advisor. We're working on very similar problems, but in a sequential fashion, where Joe was just a few years behind me in that discourse. And we've had this great opportunity to work together, starting about 6 to 8 years ago.
Tim, sorry to interrupt you. Just so you know, for some reason your slide is flashing, and I don't know if you want to stop it and reload it. There we go. There we go. I think we've got it now.
All right. Sorry about that. Yeah, the electronic gods are not cooperating. So hopefully that is good again.
So we'll run the slides. You guys just tell us when to advance.
Okay, fair enough. So I just want to make that point that we started to dabble in an area that was not new to a lot of the research in the world, but a slight twist on it, and has been what we see as very transformative in a lot of different ways. And I'll pass it to Joe to give a little bit more of an introduction there.
Thanks, Tim. So our talk is called Electrifying Combustion, and as many of you are noting in the chat, there has been a transition to electricity as the main form of powering vehicles. But electrifying combustion to us means something a little bit different. We're using plasma discharges to help combustion in ways that are that make possible a transition to renewable fuels. And we've been doing work together for many years on how you can enable certain combustion situations which weren't possible in the past, but which are necessary now in order to allow us to use zero carbon fuels, or what are called in our industry as e-fuels, which are fuels that are created directly from renewable sources and which don't have the impact on the environment that traditional fossil fuels have. So I was lucky enough to work with Tim on this when I was there at the Air Force Research Lab, and we've continued to make a lot of progress here. And I think you'll see some interesting trends in the future that will be supported by, hopefully, the work you'll see in this presentation. So Tim, back to you.
Thank you, Joe. Yeah, so the crux of all that we're going to talk about today is centered on energy. We know this is the building block of society. We as humans have tried to manipulate and harness this for a variety of our needs. And you can see them all listed there, from the most rudimentary and basic ones up through the most advanced, and some of the transportation to meet our needs to traverse the world. And our current needs are really no different, but there's other considerations, and that's become much more profound over the last, many decades, of where we want to be more environmentally sensitive and careful about how we approach this problem. So how can we meet our energy needs by also considering that, the environmental impacts that's involved? And if we look at energy, it can be categorized a variety of different ways, combustion being one of them. And you'll see why we mention this, and why it's there's a lot of perspective of that combustion is not necessarily a dying breed, meaning that it's going to be part of our lives for quite a bit of time in the near and the midterm, even as we electrify, even as we have other means such as nuclear, such as wind and solar. These are excellent means, but they're not going to meet all of our needs in society. So combustion will be around for quite a bit of time, which is why we spend so much time looking at ways to augment it. And the other thing to consider, it is the most logistically viable solution to our energy needs, as it's been for a long time. But even with that, combustion is not a 100% efficient process, even after all this time that we've been investigating it. And there's a reason for that. There's physics that drives why we can't achieve 100%, but we're sometimes really, really happy if we can only get 50% combustion efficiency out of a system. So naturally, the question is always, how do we improve upon this? And really, the way that we can do this is by augmenting it with other clever forms of energy addition. So I like to use this analogy here that Joe and I had come up with here of consider a ball sitting on top, perched on top of a hill. And that's really being the start of the combustion process, where if we just give that ball a little nudge, the ball will roll down the hill and release all this energy. So we require some little bit of a nudge to get that ball rolling, but once it starts rolling, you release all this energy and the ball goes just fine. The problem is the amount of nudging or pushing you have to give that ball is not consistent. And as we get to increasingly more demanding applications for combustion, where we have to maybe consider using alternative fuels or some very challenging type conditions, you need to push that ball very hard to get it moving. Or in another sense, the ball may not be round, and it doesn't roll down the hill, it just sort of tumbles down the hill. And we have to find a way to push it and augment it. And this is where we talk about this creative means of applying energy into the system in the form of plasma. So naturally, the next question, if you go to the next slide, is that what is plasma? So plasma is the fourth state of matter, and it is the most prevalent in all of the universe, but it's much less prevalent in our daily lives. But there's still some great examples. So if you're looking on this slide here, lightning is an excellent example of what a plasma is. And another one, which is quite beautiful in terms of the waves and the colors, is the Aurora Borealis, or the Northern Lights, as many of you know it as. And these are excellent forms of showing terrestrial plasma-based systems that are natural. But we also have many different ones which are also man-made, such as the fluorescent or neon lights that we use on a daily basis, or the spark plugs in your car. Every time you turn on your car, you're running your typical gasoline-powered engine, you have some form of plasma that's starting that engine 10 to 100 times per second, igniting and starting that engine. But let's get a little bit more, we'll drill down a little bit more in terms of what this really means. So if you go to the next slide, as we continue on this journey of understanding what plasma is and how we can deal with it, plasma is a very interesting beast, meaning that we apply an electrical potential. So we apply electricity to a gas, per se, like air, for an example. And as we apply that energy, we start changing the makeup of it, meaning that we start stripping and pulling apart molecules or atoms in a way where it can hold some quantity of energy in it. And when it holds that quantity of energy, it can then release it in creative ways. And a great example is that Aurora Borealis that we just talked about, where you can see in this picture here, these wonderful colors that are an example of the energy that's stored after you get the interaction of the solar with the magnetic field of the Earth in terms of creating this plasma in the upper atmosphere. And depending upon the conditions, depending upon what's there, you store energy in certain places, it gets released in this form in photons or light of different colors. So we can then manipulate in a variety of different ways how we produce this plasma, and we can use this to manipulate chemical reactions. And this is where it ties to combustion. So we're using this plasma to manipulate the combustion process. And that comes into play when we start talking about plasma chemistry and what we term as like a domino effect. So we apply energy, we apply this electricity to the system, we manipulate it, we store energy in different ways, we produce electrons, we produce ions. And what happens is when that interacts with all the other media that's there, these other molecules, you can get a cascading and a domino effect and a nonlinear effect, meaning that all of a sudden the energy that you put in is just a little nudge, but you get this amplified effect out the other side. And now we can manipulate how we produce this plasma, what we do with that plasma to then manipulate how we interact with the kinetics, the chemistry involved in the combustion process. So if you go to the next slide, the way that we approach this is in a way of, I'll use some analogies at least on this slide again. I'll wait for it to pop up in a moment. So how do we use this to then advance and affect combustion? It is all about efficiency. So the analogy I'll use here is that we'll use two pieces. If we take a balloon and we hold it over a head, if we do the same thing, but we then just poke it periodically, the end result is the same. The balloon stays at approximately the same location, but what we use to get it there are quite different, right? We can either hold it there or just give it this periodic tapping. And that's how we approach this problem from this plasma point of view, where if we apply energy all the time to the system, we can make wonderful things happen, but it's incredibly inefficient, and it doesn't serve the purpose in terms of meeting this efficiency or looking at improving and optimizing in systems. So we do this in a pulsed manner. So we take very, very short duration pulses that are nanoseconds in duration, so extremely short duration, but we pulse it at hundreds or thousands or hundreds of thousands of times per second. And this allows us to get the same result with a much, much lower quantity of energy into the system. So now all of a sudden we have that very clever way of nudging the ball and getting the excellent output out the other side, or maybe even possibly a better output that you could do by any other means. And the next slide gives us an example then of how we do this in our environment. So drilling down to what Joe and I are able to do in terms of providing a good fundamental understanding that's the building block approach to everything that we do in a daily life. So we're not going to take the large engine or the train or whatever you're going to talk about in terms of applying these energy systems, because it becomes very complicated. So we then decouple the system, unravel the process, and go in and say, what are the temperatures? What are the pressures? What are the flow conditions? What are those conditions that we really need to replicate? And how can we do that in a well-defined and well-controlled manner in a laboratory environment where we can elucidate the fundamental physics involved? And that's what Joe and I have spent considerable time doing. We've built up systems in the US, the Air Force, at Technion in Israel, where we can synergistically look at this process in a variety of different ways. And a great example of how this is transpiring is in what you see on this slide here, where we have this incredible need and importance of using measurement techniques. So we're doing things that have very different spatial and time scales involved. So a lot of times we have to use very, very high-speed diagnostics, measurements, to be able to see what's going on. So to get these down into the details, these videos you see here is a superposition of multiple simultaneous diagnostics of Schlieren and laser-induced fluorescence, two diagnostic techniques that are well used in the community that allow us to see and unravel and uncover the spatio-temporal understanding of how we apply energy in a creative way to a system. And if you look across this, on the bottom there, you'll see this is the rates of which we're applying this energy. I mentioned doing tens or hundreds of thousands of times per second. This is an example where the left figure is showing you where we're doing this 100,000 times per second. We're able to achieve something that you normally cannot get to happen, as opposed to when you do it at lower and lower repetition rates. So this just gives you a general idea how we can take and funnel this down to something that we can really sink our teeth into in our laboratory environment, and then build up to some more creative and practical problems. And with that, I'll pass him back to Joe, since he's going to dig down and give us a little broad perspective again, and then whittle down to a nice contribution with regard to renewable energy needs.
Thanks, Tim. So we've now been researching this method of adding energy via plasmas in these short pulses. And to get an idea of how this is useful in a more broader societal sense, we have 4 categories we're highlighting. So the first is ground transportation and fuel efficiency. So we're still, for the most part, using gasoline for our cars. Now, there is a trend for gasoline engines to go to what's called leaner conditions. This means more air, less fuel, and higher efficiency. And there's a limit to how far you can go in this direction until you start to run into a problem of the engine just simply won't ignite. And so the tools that we're using here will allow us to go to even leaner and leaner conditions, higher and higher efficiencies, less and less emissions. And it's been shown in several recent works that you can really make a huge difference on fuel efficiency just by using this more advanced ignition source that Tim and I were just have been researching and in a very similar manner to the previous slide. Another one I want to mention, going along the same trend of current technology, is gas turbine efficiency and safety on the bottom left. Bottom right. So gas turbine efficiency and safety is also dependent on the same processes as in your car engine. You cannot burn at conditions that are too far away from the most optimal conditions. And the reason for this in a gas turbine engine is because you run into certain instabilities as you start to try to increase the efficiency by reducing the amount of fuel that give a danger of, at some point, your engine not being lit anymore, or what's called flame out. And flame out can be dangerous in the gas turbine engine because it's very difficult in midair to reignite that engine. And so engine manufacturers tend to design their engines to not necessarily be the most efficient, but to be the most stable. And the type of discharges we're using can be used in 2 ways in this condition. One is to increase the stability, as we'll show in one of our studies coming up. And the other way is to increase the safety, which is applying ignition technologies which allow reignition of that engine at all conditions. And this is a concern for commercial transport, but for military transport, engine flameout is even more of a broad issue because these engines really operate at very limiting conditions. So you can increase the safety of these engines by increasing the ignition efficiency. So those are the technologies which exist now that we can improve. But really what drives me, and I'd say what drives Tim as well over the many years, are new technologies that don't exist yet. And so the 2 examples we have there are high-speed flight. So this is flight at very high, what's called Mach numbers, or multiples of the speed of sound. And we like to talk about the possibilities of going 3, 4, 5 plus times the speed of sound. And the types of engines that can allow this don't quite exist yet. Or let me say, are just still in the research phase. And part of their difficulty is that you need to ignite these when there's only about 1 millisecond of time in the engine for the flow. This creates a real challenge. And our ignition technology can provide the ignition that's needed to start these engines. And in fact, that's one of the main applications where we're starting to see a lot of interest in this technology, and it's already being considered for use. The other one that I want to talk about is alternative fuels, and that's what I'll spend the rest of this presentation talking about. So alternative fuels have been around for a long time, and the main benefit of them is that they can replace the fossil fuels we use now, but perhaps have a much, much, much reduced impact on the environment. And the one that I'll highlight here is ammonia. Ammonia, or NH3, is a fuel that's really being considered strongly in the combustion and engine worlds as a possible replacement for fossil fuels. And the reason why it's really very, let's say, popular is the wrong word, viable. It's a viable solution because, as you can see on this plot on the right, you can hold a very large amount of energy for a very long time. You can see batteries in the red circle there can hold about 1 megawatt hour for an hour to a day, where ammonia can do 1,000 times that for 1,000 times as long. So it's a very stable energy storage solution. Now, I have to say the storage capacity per unit mass is not quite that of hydrocarbon fuels, but it's much, much closer to batteries. And so when you start to talk about applications, and I'll specifically talk about aerospace applications because I'm an aerospace engineer, as is Tim, you really care about how much weight you lift and about how much energy is in that weight. And that's why while we see electrification of cars, you're not really seeing that for air travel, not for large vehicles. And the reason is the battery, with the amount of energy that it has, is just too heavy to carry. And in order to make renewable energy possible on aircraft, you really need to switch to what we call an e-fuel, ammonia being an example. So we call these e-fuels because they're created from renewable energy. And as you can see on the diagram on the bottom right here, yes, we start with hydrogen, and hydrogen can be obtained, and the majority of it is now obtained from fossil fuels extraction, where hydrogen is a byproduct of that. But the hope is that renewable energy will be used to create hydrogen through a process called electrolysis, or hopefully a more efficient process that can take over that. And this is generally known as the hydrogen economy. So there's one benefit that you can create hydrogen directly from renewable energy. You could also create it from surplus energy. And this goes to the energy sector. The energy sector is largely switching to renewables, which means that you have fluctuations in your energy production. If it's windy, if it's sunny, you have a lot of energy that's created. On the other hand, if it's shady, if the wind's not blowing, if the river happens to be low, you don't get as much energy as you need. And so the idea is to have a large energy storage bank that you can count on for when you have too much energy, you can store it and not waste it. And if you have too little, then you can turn on this stored energy and be able to use that. So the idea would be for hydrogen to be created in this way. The problem with hydrogen is it's very, very difficult to store it. It's very, very difficult to transport it. If you wanted to use it on a plane, if you wanted to use it on a ship especially, or on a truck, it's very difficult because it needs to be stored at very high pressures. It leaks very easily. It's highly explosive. So hydrogen has a huge amount of issues needing to be solved. Luckily, ammonia can be made just from hydrogen and nitrogen from the air. And it has a massive infrastructure already. So the benefits are when we burn ammonia, we create no greenhouse gases if we do it properly, but certainly no CO2. It has a high energy density, almost as high as fossil fuels, much higher than hydrogen. It's easily stored in a stable way. It's relatively safe. And I say it's relatively safe largely because of the next point, which is it has a large-scale existing infrastructure. In fact, ammonia is the second most produced chemical on Earth. About 5% of, in terms of volume, how to phrase this?
That gives us.
We have about 5% production of ammonia compared to oil, meaning of all the oil that we use, we also use about 5% the amount of that in ammonia. And that's saying a huge amount in terms of how large the infrastructure is. I want to emphasize there's ammonia storage everywhere. And it's mostly used for agriculture. So because we're so good at using ammonia in our world, and because it's easily produced from renewables, like particularly hydrogen, it's considered a really viable option for air transport, for marine transport, and for energy storage in terms of a renewable system. And this is really critical to going to fully renewable. So could you move to the next slide, please? So I'm going to highlight a study that Tim did with a colleague named Wenting Sen, who was another colleague of ours over at Princeton. And this was a study that showed how you can increase the stability of ammonia. So ammonia sounds really great on paper. The problem is when you try to burn it, you find that it has a very low, what's called flame speed. That's how quickly the flame can travel in a mixture, and it's about 25% of that of fossil fuels. And so it tends to be very unstable. So what you can see in the images on the bottom left are images of an ammonia flame in a gas turbine type combustor. And you can see it's very unstable on the left.
What you
but when you apply a plasma discharge, similar to the ones that Tim was talking about, and you leave it on continuously, you see that you can stabilize this flame, and you can stabilize it at much higher flow rates and much wider range than you could without the plasma. And not only does this have a benefit in terms of enabling the use of ammonia in this type of engine, it also has the added benefit of reducing the emission of nitric oxides, or NOx, which is a harmful pollutant and one that's strictly controlled. So because ammonia has nitrogen in its fuel molecule, NOx is a very important problem to solve. And with a plasma, Tim saw that you could reduce by 35% or so how much NOx you produce.
You basically capture.
Okay, so this was a very nice study showing the feasibility in a gas turbine combustor. If you can go to the next slide, please. Work that's been going on in my laboratory has been to try to understand how this plasma chemistry interacts with ammonia. So what we've done is we've built a numerical model for how plasma interacts with ammonia. And I'll give a second for the slide change here. Okay, so what we have here is a graph that shows on the x-axis and on the bottom axis increasing pulse frequency. I'm talking about the image on the left.
Sorry?
And what we've shown is that we can reduce the temperature needed to ignite ammonia by applying this type of high frequency discharge. And this allows us to use ammonia as a fuel in almost any engine just by changing how we ignite it. And if we ignite it properly, we can get around the problem of the difficult burning conditions that this fuel poses. And we've shown that in a number of conditions, and we've shown that we can reduce the time for ignition by a factor of 10. So essentially, in these two studies, for ignition and for flame stability, we've shown that we can enable ammonia in today's engines just using these plasma technologies we've been talking about. And this will allow us to switch a large amount of the infrastructure we already have to a fuel that will release no greenhouse gases, just by changing how we apply energy to that system to sustain it. And this is reminiscent of this pentagon that we showed, the difficult shaped ball that we want to push down the hill. Ammonia is a very difficult ball to push down the hill, but luckily these tools that we've been developing for many years are already a solution that we've shown is viable for transitioning to this type of fuel. If you can go to the next slide, please. So to take an even deeper look into this, and I hope it's not too much chemistry for you all, but this is what we do. This is some of the results of this model that we built, this computer model that is able to predict what will happen when we apply plasma to ammonia. Now, in the red arrows, we see how ammonia typically ignites without the use of plasma. And the green arrows show the reactions that happen when you do apply a plasma. So as you can see, for thermal ignition or without a plasma, the main way that ammonia reacts at first is just with oxygen in the air. And it creates NH2, which is the first what's called radical formed from ammonia, plus another molecule called HO2. And these are known, especially HO2, to be quite slowly reacting. Now, as soon as we apply a plasma, this reaction is completely inactive, meaning we sidestep this entire process. Instead, we go to much faster rates for ammonia plus O atom and ammonia plus H atom. The ammonia plus O atom and the ammonia plus H atom are only possible because we've created these atoms by applying the electrical discharge. And then in addition, we have our electrons, which are directly part of the plasma, attacking the fuel and accounting for 20% of the fuel decomposition. So to simplify this whole story, what we've done is we've changed the entire way that ammonia ignites by introducing a small amount of plasma energy into the system. And we sidestep the slowest processes, unlocking the potential for ammonia to react quickly and more similarly to today's hydrocarbon fuels, which really allows us to consider transitioning our current infrastructure over to an ammonia-fueled infrastructure without having to rebuild all the engines on Earth. So this is really the goal here, is how to enable this fuel in today's infrastructure in order to meet the renewable energy demands that we know we need right now. Okay, so with that, we'll move on to our summary slide. So generating and controlling plasma discharge is essentially what we are doing with pulse plasma systems. We are able to manipulate the plasma and create the molecules and atoms and the excited states that we would like in order to have the chemical reactions which will drive our system forward. And we can apply that power using this pulse technology in a way that doesn't require a huge amount of energy input. And the reason that's important is because in an energy system, you don't want to use the energy to keep the system running. You would like to use a tiny percentage of the energy to sustain the process. And in all the cases we've shown, we're just talking about percent level energy addition, but that makes a massive difference in how the fuel is stabilized or ignited. And the fundamental experiments that we do in our labs is really paving the way to show the feasibility of these alternative fuels and are pointing to what practical applications can then be developed from these ideas in our lab. So I'll pass it back to Tim if you have anything to add about the summary, but otherwise that's our spiel.
Yeah, Joe, I think you did an excellent summary of what's going on, and I think it's I think to point out one thing again is plasma has been applied to a variety of different systems, and I even see some of the ones in the chat. Right, plasma is quite an interesting beast to be applied in a variety of different ways, and it's been applied to combustion for 30-ish years now in a variety of different situations. And again, the biggest stumbling block in this has been, how do you put it in the right way? Like, how do you do this efficiently? So we've known for a very long time that you can add energy into the system and it's going to make it work better, but how do you do it in an efficient manner? And that's really where this pulsed power technology that's developed tremendously over the last 10 to 20 years has enabled this to happen, meaning that we can be in this position where we can commercially buy these type of systems and use them in the lab. They're not finicky research grade. They're really well developed and robust devices. And that allows us to now unlock the potential of doing this in an efficient manner that we didn't have 20 years ago. Was not possible. 10 was just on the cusp, and today this is a reality. So I'll end with that and pass it back to the hosts.
Thanks so much. If there was any concern that the Jersey boys are just a bunch of singers, I think we've disproved that today. Really, you've introduced us to so many potentially groundbreaking concepts here. But I have to begin with ammonia. I feel like we've buried the lead here. I kept waiting for a but at some point, and at one point I saw Tim grinning a little bit. Tim, what, as you were listening to Joseph, part of the conversation on the potential for ammonia, how close are we on this? I mean, as a viable alternative fuel?
I don't think too far away. I think this is some of the earlier works in terms of the forcing function that's needed to enable ammonia to be used in a realistic environment. So I think there's enough of a proof of concept there. This is not going to be in the next couple of years that you're going to have ammonia. You're not going to fill it with ammonia at the gas station in the next couple of years. It's a little far away from that.
That was my next question.
Maybe Joe has other thoughts on it, but I think it's a little ways down the road. It is on the earlier stages, but I would say that I'm a little struck by how easily we're able to show in a short period of time the potential. And a lot of times we struggle for a long period of time of how to attack the problem. And that, I think what was shown in in a matter of 6 months to a year of working on a project versus spending 5 or 10 years to get to the same point. I think that's the encouraging aspect. The devil's always in the details. So as things progress, there's certainly things that could come up that might preclude its application, but there doesn't seem to be any major stumbling blocks. Maybe the biggest stumbling block is it's the shift in how we think about it, right? There's always a lot of political pressures, socioeconomic pressures that we have to consider that might, and do a lot of times, stop the progression of things, right? Technology can't always just solve all and make it happen. There are these other pressures that are involved. And there's certainly those will come into play here. But this seems like there's a significant promise to making this a reality, and there will be a continual movement in this direction. We're not the only ones working on this. There's many groups that have looked at ammonia for many years as a viable source, but there's been these stumbling blocks that I think we're starting to overcome.
And there's a question from the chat about the toxicity. At an industrial scale level, is that something to worry about, or just like anything else, a consideration?
Maybe I'll let Joe chime in on that one. Joe, you have a comment on that in your experience?
Sure, I do. And toxicity with ammonia is a significant issue. But listen, there's issues with many of the fuels we use. So let's consider that we're going to switch from gasoline and other hydrocarbon fuels. Okay, let's live in this world for the moment. What are our alternatives? Right, we still need to carry higher energy density fuels, let's say, on airplanes, on ships. These things are going to be around. Me personally, I really do think we're going to electrify cars, and you're going to say goodbye to the gas pump. So I'm thinking more in terms of aerospace applications and maritime applications, things where you need to carry a large amount of fuel and you really care about how much that weighs. And then on the other side of things, I'm also thinking about the energy storage issues. And for anybody who's been keeping up with renewable energy, really the stumbling block isn't that we don't know how to create the energy. The stumbling block is we don't know what to do when we have too much or too little of it. It's really a problem when you start talking about 50% renewable, 80% renewable. It becomes the major stumbling block. And batteries just haven't been shown to cut it, let alone the issues with rare earth metals and recycling of batteries. I mean, these are real issues. But in terms of the energy density and in terms of the long-term storage capability, being able to chemically store this excess energy is really one of the most important problems we need to solve. And in that case, we're talking about ammonia toxicity, but we're not talking about you being maybe, unless you're an electrical system, let's say maintenance person, but you going to your car, I don't see that being the main application. So these are going to be handled by professionals. And as I said, I mean, we produce 5% of the total oil production by volume in ammonia volume. And that's just massive in scale. So we have the skills, we know how to store it, we know how to transport it, we know how to handle it. And I mean, this is used on everyday farms in large scale at this time. So the toxicity is an issue, but it's actually a solved issue, in my opinion.
So what do they actually use it for in agriculture, given that it has such a large presence?
It's either used directly or used to create fertilizers.
Fertilizers. Okay. And people are asking already, is there a way to invest in this kind of development? I assume if there's an industry that's distributing it in agriculture and other uses, that it is treated like any other commodity, or what is that like? I understand that it's still at an early stage in terms of thinking about it for fuel, but are there some, do you know if there are actually some commercialization efforts yet, or is it too early?
There are commercialization efforts. I'm sorry, I don't have a reference for them with me right now, but there is a large-scale project going on right now in Europe to run an entire cargo ship purely on ammonia. Mm-hmm. There's a company over in England, I believe they're called Reaction Systems or Reaction Engines. I'm sorry if I'm not getting the name right, but they're creating a catalytic converter to do exactly what we're talking about, enhance ammonia's ability to be used as a hydrocarbon fuel. I should say the main stumbling block are the things I mentioned in terms of using it as a combustion fuel, which is to be able to burn it efficiently, being that its burning characteristics, its combustion characteristics, as we call them, are much degraded compared to hydrocarbon fuels. But that's why we're developing these technologies to enable it. And that's really what's changed in its consideration over the years, why you haven't seen it under consideration before. But now that we're really earnestly trying to switch away from combustion and the clock is running, you start to see these kind of ideas that before may not have been thought of as the most promising, now becoming really very interesting. And I should say, I was just looking, and on our largest journal in our field on combustion and flame, ammonia is the #1 paper right now. So there's a big change happening there. I'm sorry, I'm not sure about investment opportunities.
We're a nonprofit. We're not really looking to commercialize anything yet. But I do think it's telling, as you're saying, that if it's getting this much resonance now in your field, the fact that we still have a very parochial notion of ammonia as a household cleaner, it certainly should not be the defining factor.
To be honest, and Wayne, I'll jump in really quickly. Ammonia actually might not be so far away from your everyday activities as you think. For most large-scale HVAC systems, they're running on ammonia right now. So it's kind of everywhere.
Mm-hmm. Interesting. So one question is about the NO2 residue in the engines. Is there any way to collect or reconstitute that, or is it just lost?
NO2. Well, Tim, you did the study on NOx output. I'll let you field this one.
Yeah, so I mean, in general, we deal with NOx is nitrous oxides, NO, NO2, and other nitric oxide compounds are produced in every combustion system. And how we usually deal with it is we use a three-way catalyst. So you have a catalytic converter, let's say in your gasoline engine powered car or vehicle, where you try to react those gases out downstream and convert them back down so that you minimize the amount that's coming out the exhaust pipe. So there are a variety of different ways that you can do this. Now, you probably notice if you're astutely looking at the numbers there, the numbers like the thousands of parts per million might seem a little striking in that specific situation, because a lot of times things are controlled to tens to hundreds of parts per million level, right? So that's a very, very small amount. That's 10 to 100 in a million molecules there are the ones that are nitric oxide. So there are means of doing this, and I think that it's not far-fetched to be able to manipulate catalyst or catalytic technology in the exhaust to be able to do this. Additionally, there's a lot of efforts with plasmas using to reduce pollutants. So take your normal engine, your normal gasoline engine combustion process, and applying these types of plasmas in the exhaust to manipulate the chemical composition in a similar manner to what a catalytic converter does, and has shown great promise, used in diesel engines and gasoline engines. So that's another interesting example of how you could potentially use this type of pulse power plasma technology in concert with the catalytic technology to be able to reduce those down to probably the levels that make sense from a commercial application of such.
And I just want a little bit. Sorry, Wayne.
No. Please go ahead.
I can add a little bit to what Tim said, but some efforts on gas turbine combustions that have come out just in the last 2 years have shown that through clever fueling strategies with ammonia, you can really get those ppm numbers down to the single digits. It's in a little bit of a different way than we're used to burning fuels. But if you design your combustor specifically for ammonia, you can reduce the ammonia down to very, very low levels. So it's feasible. And whether you use a catalytic converter or try to do clever things with your combustion device, this is possible. It's not a roadblock or at least not a debilitating roadblock, let's say.
Joe, I just have to go back to a comment you made earlier that the potential, at least, for the high-speed flights is that we could get to 3 to 5 times the speed of sound? Give me another sentence or two on that. What is that going to look like? I did hear that you said there's a limitation on the technology on the engines, that we don't have the engines to be able to produce that now. But what are the next steps in that development heading in that direction? Because that sounds pretty fast.
Well, this is a field called hypersonics. Actually, it so happens that Technion is in the process of forming a Technion high-speed flight center to focus on just these issues, which is a really nice development that you'll be hearing more about in the next few months. But this has been a big worldwide effort to try to create engines that can fly Mach 5 plus. Now, Mach 3 plus, this technology has been around since maybe, if anybody knows, the SR-71 or the Blackbird, the famous plane. And now it's becoming a topic again. And actually, I've just been reading that United Airlines signed a contract to buy a small fleet of not hypersonic, but high supersonic, or Mach 2 or 3 planes. And so it's becoming this new age, let's say, of high-speed flight. And there's many different drivers for that. One actually is what you mentioned in the introduction, which is space entry. So now that there's many companies starting to go out on their own and create new engines or new vehicles, maybe not new engines, for space entry, actually these very high-speed air-breathing engines can serve as a first stage that's much less energy, much more efficient, much more practical if we're going to think about a time when it may be somewhat normal to fly into space. And one of the enabling components of these engines is these ignition devices. And the reason for that is because you simply need to accelerate the engine already to high Mach number before you can even ignite it. And then you're talking about igniting an engine with a very high speed flow going through it. And you need really a serious change from a type of spark technology that we've had up until now. And that's been one of the drivers of our research in this area.
Well, guys, we are coming to the end of our hour, but I just want to give you each an opportunity to be a forecaster. 10 years out, just Tim, I know you said we won't be pumping ammonia at the gas station, in the next couple of years, but 10 years out, one prediction in your field that you think in terms of, widespread application that we might actually see, whether it's supersonic flight or alternative fuels. What's one thing that you think you could see happening 10 years from now?
Hey, how about I'll go first? And since we were on the topic of high-speed flight, so I really think that we're going to see supersonic air transport is coming into play in the next decade again. There's a lot of momentum in that direction now. We used to do this with the Concorde flying back and forth across the Atlantic. That was going at 2 times the speed of sound, over 2 times the speed of sound. But it wasn't very efficient, and it was quite loud, and had a lot of problems doing it over land because of sonic booms, which is a whole other discussion. But the name of the game is doing it in a more efficient manner, and technology has progressed enough that from the 1960s, 70s technology that enabled that to be able to make that a reality. So I think it's going to be a reality either in the business or commercial sense that within 10 years you could be seeing some faster than the speed of sound flight again in a commercial sense.
Joe?
I would say that I'll take a different route and talk a little bit about energy. I think we're going to see a very different type of energy landscape than we used to. And the main thing that will characterize it is diversity in our energies, whether that's how our cars are run, whether we have mostly electric cars or a mixture of cars running on different types of fuels. With air travel, there's already a large mix of alternative fuels that planes and fleets are starting to fly on. And then with energy generation, there are just so many, right now our world runs on 80% fossil fuel combustion, right? And that number is going to and needs to drop significantly. And what replaces it, there's not going to be a silver bullet. There's going to be many, many different energy solutions, energy storage solutions, energy generation solutions. And I think that what you'll see is a very diverse landscape in terms of how we how we get energy, how we store it, and then how we eventually use it than what you see now. And I think ammonia and these types of plasma technologies will play a part in that.
Wow, we covered a lot of ground today. So grateful. We do this twice a week on different topics. This is our third in high science, and the reactions and responses from our audience are really so appreciative for your sharing your time and giving us a little glimpse of what you work on day to day and what we may be seeing and experiencing in the coming years. And we're so grateful for your contributions to science, to humanity, to really the progress of humanity in your respective fields. We will be back again on Sunday. We're actually going to be in Haifa again, this time at Haifa Museum of Art with a program that is going to pair an artist in Haifa and an artist in Boston, looking at how contemporary art examines identity. And so we think that this would be a great opportunity for the weekend to do something fun and light and creative. So we hope you'll join with us again. I will extend my thanks again to the Jersey boys for their great work and presentation today. And I don't know about you, but I'm going down to the basement to find the ammonia. Hope everyone has a safe and wonderful week. Thanks again. Greetings. We enjoyed having you here.
Thank you, Wayne.
Yeah, thank you very much.
Watching.